Okay, let's continue our discussion. As mentioned, for square foundation, you have this equation, and for equation for the ultimate bearing capacity, and for the ultimate bearing capacity for circular foundation, this is the formula that you will be using. So based on the formula, you have the bearing capacity factor, N sub C, N sub Q, and N sub gamma. So you can make use of the formula that was presented a while ago. However, there is a table for the bearing capacity factors for N sub C, N sub Q, and N sub gamma. You just have to know the value for our phi, which is our angle of friction. Then afterwards, once you have the angle of friction, you can immediately know the value for our bearing capacity factors. And we have here our modified ultimate bearing capacity factors. Our prime represent that this is a modified equation for strip foundation or continuous foundation, for square foundation, and for circular foundation. So for our modified N sub prime, C, N sub Q prime, and N sub gamma prime, that can be supplemented with the values from table 3.2. And why is this was modified? This was the Terzaghi's bearing capacity equation. It was modified because he take into consideration the effects of foundation shape, the depth of embedment, and the load of inclination. So for that, this is the modified bearing capacity factors, N sub C prime, N sub Q prime, and N sub gamma prime. Just know the value for our phi prime, which is our angle of friction. For the factor of safety, so when we talk about factor of safety in engineering, it is also known as safety factor. It expresses how much stronger a system is than it needs to be for an intended load. So to calculate the gross allowable load bearing capacity of shallow foundation, it requires the application of the factor of safety to the gross ultimate bearing capacity. So this is the formula. This is the allowable load bearing capacity, which is equal to the ultimate bearing capacity over the factor of safety. However, some practitioners, some engineers prefer to use the factor of safety with this expression: net stress increase on soil is equal to the net ultimate bearing capacity over the factor of safety. So the net ultimate bearing capacity is defined as the ultimate pressure per unit area of the foundation that can be supported by the soil in excess of the pressure caused by the surrounding soil at the foundation level. So if the difference between the unit weight of concrete used in the foundation and the unit weight of the soil surrounding is assumed to be negligible, so you have this expression that the net ultimate bearing capacity is equal to ultimate bearing capacity subtracted by our surcharge. So you have this equation, and if you wanted to compute our net allowable bearing capacity, you can have this equation Q sub U minus Q all over the factor of safety, wherein for the factor of safety, we have considered at least 3 for all cases. So this is another type of factor of safety for the bearing capacity of shallow foundation. So this is what we call the factor of safety with respect to the shear failure, FS, with respect to the shear failure, wherein the factor of safety with respect to the shear failure is equivalent to 1.4 to 1.6. So is desirable along with the minimum factor of safety of 3 to 4 against gross or ultimate bearing capacity. So for the procedure on how to calculate the net allowable load for a given factor of safety with respect to the shear failure. So this is the procedure. Just follow the procedure so that you can compute for the net allowable for a given factor of safety with respect to the shear failure. So we have here a sample problem. It states that a square foundation is 5 feet by 5 feet in plan. The soil supporting the foundation has a friction angle of phi prime equal to 20 degrees and C prime is equal to 320 pounds per square feet. The unit weight of soil, gamma, is 115 pounds per cubic feet. Determine the allowable gross load on the foundation with a factor of safety Fs of 4. Assume that the depth of the foundation, d sub f, is 3 feet and that general shear failure occurs in the soil. So we are going to have this equation. Allowable ultimate load bearing capacity is equal to 1.3 C prime n sub C plus Q n sub Q plus 0.4 gamma B n sub gamma. So for this one, this is the equation for the formula for a square foundation. So we have to identify our n sub C, n sub Q, or n sub gamma, which is our bearing capacity factors. Having our phi is equal to 20 degrees. So these are not the values. Then afterwards, you simply have to substitute the given values so that we can obtain our ultimate bearing capacity, which is 10,736 pounds per square feet. So if you're going now to compute for the allowable load per unit area of the foundation, so you simply have to divide our ultimate bearing capacity with our factor of safety given, which is 4. So you obtain approximately this is equal to 2,691 pounds per square feet. So the total allowable gross load is, you have Q, this is the total allowable, capital Q represents total allowable gross load, which is equal to our allowable load per unit area of the foundation, since multiplied to the area of the foundation, since this is square, so B squared, which is equal to 67,275 pounds. So we have here a modification of bearing capacity equation. So modification of bearing capacity equations for water table. So we have now the presence of water table. A while ago, there was no water table. Now there is water table. How to compute for the bearing capacity equation. So we have 3 cases here. So if you're going to observe the first case here, for case 1, our water table is above the base of the foundation. For case 2, the water table is below the base of the foundation. So for case 1, if the water table is located so that our D1, this is our D1, is greater than 0 but less than DF, this is our DF, which is the depth of embedment of our foundation, the factor Q in the bearing capacity equation takes the form. So this is our Q, which is referred as effective surcharge. You have this equation. And of course, for our parameters used, so we have here identified the definition for each. So for this one, also the value of gamma in the last term of the equation has to be replaced by gamma prime, which is equal actually to the saturated unit weight subtracted by the unit weight of the water. For case 2, for the water table located so that our D, where is our D? This is our D. D is the distance. We are now on case 2, meaning to say the groundwater table is below the base of the foundation. So our small letter D is from the base of the foundation towards the water table surface. So if D, small d is greater than 0 but less than the width of the foundation, which is our B, our Q is equal to gamma times this of 1. So in this case, the factor gamma in the last term of the bearing capacity equation must be replaced by the factor, and this is now equivalent to this equation. So the preceding modification are based on the assumption that there is no seepage force in the soil. For case 3, meaning to say our water table is located so that our B is greater than our base, the width of the foundation is less than our the small letter D, so the water will have no effect on the ultimate bearing capacity. So we move on now to the general bearing capacity equation. Computation for the ultimate bearing capacity, but this was now introduced by Mayer-Off. For Mayer-Off equation for the ultimate bearing capacity, this is now for the computation for the case of rectangular foundation. In our previous discussion, we only have for Terzaghi, for continuous or strip foundation, for square foundation, and for circular foundation. So for this one, we are now on the ultimate bearing capacity for rectangular foundation. This was suggested, or this was introduced by Mayer-Off. So for this one, there is an additional capacity factors. So we have now the shape factors, depth factors, load inclination factor, and of course we still have our bearing capacity factors. So for the bearing capacity factors, we simply have to use the formula or the table that was given a while ago. For the shape factors, depth factor, and load inclination factors, you have these equations. For the shape factors, you simply have to substitute the given values for each variable for the parameters. Of course, for the bearing capacity factors, as mentioned, you make use of the table a while ago presented. For the depth factors, you have this equation. So for our sample problem, a square foundation has to be constructed as shown in the figure. As assume that our gamma is 105 pounds per cubic feet, saturated unit weight is 118 pounds per cubic feet, our d sub f is 4 feet, d sub 1 is 2 feet. The gross allowable load is, with a factor of safety, is 150,000 pounds. So the standard penetration resistance and sub 60 values are as follows. So we are given with the N sub 60, which is known as the standard penetration resistance with respect to each depth of our foundation. So this is the illustration or the figure for our square foundation. So what we're going to do is to determine the size of the footing. So you simply have to get the value for our parameters first, then afterwards this is now the equation for the phi, or the angle of friction. And to present well our equation or our solution, it was tabulated from its depth 5, 10, 15, 20 to 25. We presented the N sub 60, then compute for the vertical stresses. Then of course, compute for our phi, which is our angle of friction, using this equation. Of course, for this one, this is 2 coming from d sub 1 multiplied to our 105, which is our gamma, then plus 3 saturated, since that depthness is saturated. This one is 3, so this is saturated, so meaning to say you have 2 times 118 is the saturated unit weight subtracted by the unit weight of the water, so you get this equation. Then afterwards, with the succeeding, you simply have this value add to, you multiply 5, the depth times the saturated unit weight subtracted by the unit weight of water is equal to this, then, and so on and so on. So you get also the angle of friction, the average angle of friction, which is 34 degrees. So from there, you can compute now for the allowable bearing capacity, which is equal to our gross allowable load, which is 150,000 over b squared. This is the area, the b squared, which is referring to the area. Then from that, you can have this equation, substitute. You have allowable is equal to Q sub U all over factor of safety, and you use this equation. Then afterwards, you get the capacity factors. Then after you have computed, you can solve for our effective surcharge. You can compute for our allowable load. And you have now this unknown B, which is the size of the foundation. So from there, this the value a while ago that we have identified can be equated to this equation, and solving simultaneously, you can solve for our B, which is now the width of the foundation, which is 4.5 feet. So that ends